Good afternoon, everyone. My name is PRAJWAL and I am from Goa College of Engineering, GEC. So, today I am going to present you my master's project, which is in development of coil energy harvesting from the ambient magnetic field. So, my college mentor is Mr. Sangam Borkar, and my other mentor is Raj Sekharan sir. So the main objective of this project is to develop a coil to harvest energy from the magnetic field of the transmission line to replace the 3.3 volt battery, which and this particular project it is applicable in the substations directly, where the houses are getting electrified. So this is the brief overview of my project. So here in this energy harvesting device, the main coil is going to come, which will be placed at a certain distance, like 2 centimeter, 3 centimeter from the pole, which I will be from the transmission line that I will be explaining further. And this is the energy conversion unit. So whatever AC power that is going to get generated from this side, it will be transferred to this conversion block, and from conversion block a full wave rectifier mechanism will be used to convert it into a DC part. So once this DC it gets converted into DC, it will be stored in a supercapacitor, and from this supercapacitor it will be used to power an embedded device. So you can go through this particular energy harvesting device. So the energy harvesting device contains of core which is made up of silicon steel material with copper windings around it, and the energy storage device is nothing but a supercapacitor that will be used in a range of few farad to farads, and the embedded device temperature sensor, pressure sensor, humidity sensor, such sensors will be used. Now moving to the next slide. Yeah, the energy harvesting device. Now theoretically, for a toroidal shaped core, we have got the voltage of 90 millivolts. As you can see in this 90 millivolts I was able to obtain theoretically. So here is the formula for this, the basic formula: height of the core into the permeability of free space into relative permeability into the number of turns. So these are the number of turns. Okay, this 1320 turns. F is the frequency 50, it will be idle. I is the current passing through the transmission line, which I will be explaining to you. W is the width of this particular core. D is the distance between this core and the transmission line, which I will be again further explaining you when I will be showing you the experimental lab setup. Now moving on further. Yeah, so this is the transmission line which I was talking about. Okay, and the D is this 2 centimeters. It is kept, this is my core, this is my experimental core from where I'm going to harvest the energy, and it is kept at a distance of 2 centimeters, and input is given of 200 amperes from this transmission line. So when 200 amperes is transmitted from this line, a certain amount of magnetic field will get generated around this particular transmission line. So this magnetic field around this transmission line, we will be using it to harvest from this toroidal core. Okay, so for experiment purpose, we had tried it for 200 milliamps, 500 amps, 750 amps at a distance of 2 centimeters. As you can see, this small gap which is there, it is at a distance of 2 centimeters from this transmission line. So at 2 centimeters for 750 amps we are getting 60 millivolts. Here you go, you can see the digital meter readings now. Yeah, so these are the digital multimeter readings. For 750 amps we are getting 60 millivolts, and theoretically we are getting 90 millivolts. So there is a drop of 33% due to heat losses, uh, magnetic saturation and all this stuff. Yeah, so these are the different cores now which I have tested. The previous one where I tested, it was for 1320 number of turns. So for this, now we are having 8500 turns, 15,000 turns, and 4400 turns. So as we increase the current, the VI characteristic graph that you can see. So for 8000 turns, you can say the blue line is indicating for 8500 turns, as you can see, and as we are reaching 1300 for 8500 turns, the V induced is 1.1 volt, and when we are taking 15,000 tons for the same silicon steel core, we are able to induce 1.5 volts, 1.54 volts, which is a significant increase just by increasing the number of turns. So the N, this particular factor, plays a crucial role in inducing the voltage from the magnetic field from the transmission line. Yeah. So usually what happens is 750 amps, 1300 amps, it's not feasible. So we came across a new proposal design, which is a cylindrical core. So as you can see, this is a cylindrical core. The previous were the toroidal shaped cores. Now this is a cylindrical core. So from this is the transmission line. So what is going to happen now in this? A silicon steel core of cylindrical shape will be placed at a distance of 2 centimeters from this core, from the transmission line. Okay, so now I will be showing you the theoretical calculations for cylindrical core. Yeah, so these are the theoretical uh, calculations. So n is the number of turns. Okay, you can refer to my, you can pause the video and go back few seconds, and then here you can see the formula. So n is the number of turns, W is the frequency, permeability of the free space, and B is the magnetic field, A is the area of the core, D is the distance from the conductor, F is the frequency, and current through the conductor. So in this, the main purpose of taking the cylindrical core is, here we have to just give 50 amps, whereas in the toroidal core we have to give 750 amps, 1300 amps. So theoretically now we are getting for 4600 turns. So as the number of turns increases, the copper also will be the material that is going to be used, that will be also be high. So and plus the getting 750 amps is also difficult. So that is why we are going for cylindrical core now, and theoretically we are getting 5.81. So this is the simulation which I have done using LT Spice. So this is the current transformer mechanism that has been developed. Okay, and there is an input of 50 amps that has been given, and this is the full wave rectifier mechanism. As you can see, there is one diode and there is another diode over here. So this indicates the full wave rectifier mechanism, and whatever is the DC output, it will be stored in this supercapacitor of 2 farads, and this 2 farad, the voltage that will be stored will be very minimum. So this particular capacitor will give its energy, or whatever is the storage charge, it will be giving it to the voltage booster LT1371, and at the end we are going to get amplified output. So I'll be showing you the simulations now. Yeah, so these are the results, input waveform in the simulation circuit. So 50 amps I have given at the input, so 50 amps I have given, and this is the output across the supercapacitor, which is 2.4 volts. 2.4 volts. Okay, you can, if the graphics, if the image is not clear, you can refer to my research paper. Okay, I'm moving to the next slide. Yeah, so this is the output across the, this is an amplified output. In previous output we were getting 2.4 volts, but now after amplification we are getting 5.75 volts. As you can see, 5.75 volts we are getting. and the conclusion from this particular experiment. So with the toroidal core, the voltage induced is 60 millivolts with 1320 turns of enameled copper wire on toroidal geometry at 750 amps. Now, the conclusion that we have made, the current passing from the transmission line and the number of turns around the core play a significant role in voltage induced in the core. The theoretical calculations and practical readings for the toroidal core are approximately same. So the proposed design of the cylindrical core with theoretical calculations and LT spice for 5.81 volts and 5.75 volts are performed. The future extension will include integrating an energy collecting system using easily accessible modules and developing better gadgets. So now that we will be using cylindrical core for this experiment further for next 6 months. So this for the future gadgets, for the embedded devices to power up, it will be used directly using the cylindrical core such that the amps within 50 amps to 100 amps this experimentation is possible. So now I'll be going to the references. So these are the references of my research paper. Okay. Yeah, thank you. Have a nice day.